For number 16 in the 5.4 Achieve homework assignment, it's one of these problems where we have to integrate on a definite integral this time from 1 to 4, but it's one in which we have to remember to do the algebra before we do the calculus. There is no such thing as the integral quotient rule. So I have to get rid of this quotient by distributing that x to the understood 1/2 power in the denominator into each term in the numerator. That's going to give me 5x to the positive 1/2 plus 2x to the negative 1/2. Once you've done that, then we can pretty easily do our power rule. The first term is going to become 5x to the 3/2 times 2/3. That's where I got the 10/3 x to the 3/2. The second term is going to become 2x to the positive 1/2, and then divided by 1/2, that 2 is going to become a 4x to the 1/2. We're now evaluating that between 1 and 4. When I plug in a 4, I get the square root of 4 is 2, 2 cubed is 8. The first term is going to be 80/3. Plug a 4 into your second term, you're just going to get 4 times 2, 4 plus 8. So for my upper limit, I have 80/3 plus 8 minus the lower limit. Well, when you evaluate each of these at 1, you're just going to get 10/3 plus 4. So we subtract the group 10/3 plus 4. I took 80/3 minus 10/3 is 70/3. We know the 8 minus 4 is 4. So I thought of this as 70/3 plus 12/3 for 82/3. We'll check that here, 82/3. Check answer. Oh, and sometimes Achieve does this. It's typically when it happens, it's because it's been open too long. I created the first video with the first 15 problems, then I went away and I came back for these, and I think because of that, it's just been open too long. So when that's the case, just go ahead and log out. You'll see for my YouTube video processed there, that's what I was doing in the meantime. But just go ahead and log out and then go back into it, and it should be fine. So I'll log back in here. Boom. When we go into our class, the quickest way to get into it, I always go over to view all assignments and then the 5.4 assignment. Now, when I first enter in 5.4, you will go straight to the assignment. Mine goes to a creation page, but to see the page you get, I just need to go student preview. And this is the page that will load up for you. Now, hopefully we won't have any issues like what happened last time. Notice the same problem, and to this problem we had the solution 82/3. I'll put that solution in again, and it should work this time. It does. Okay, now next up we have an exponential function in there, ridiculously easy. We know that the integral of any exponential function is just that exponential function. This time we're evaluating between 0 and 5. Be careful about that 0. So often you can just ignore it. You can't in this case. When I plug in the 5, I'll get 5e to the 5th. But now when I plug in that 0, I'll get 5e to the 0, which is 5 times 1. So you'll get 5e to the 5th minus 5 for our final answer. 5e raised to the x, not to the x, to the 5th. And then minus 5. Should be final answer. We check that, correct. For 18, now in the last one I said the integral of any exponential function is that exponential function, which is true, but remember, yes, the integral of any exponential function is that exponential function, but just like when we take the derivative, there's a chain rule component. In the last one, the derivative of that exponent was 1, so I didn't have to worry about it. This time, the derivative of that exponent would be -6 with respect to x. So I'm going to have to divide my integral of an exponential function is that exponential function divided by the derivative of its linear exponent, which in this case is going to be -6. We're now evaluating between 0 and 1. When I plug the 1 in, I would get e to the 1 minus 6, e to the negative 5th power divided by negative 6, minus the lower limit. When you plug the 0 in, you're just going to get e to the 1st, or just e, over negative 6. But now I'm subtracting a negative. I know that that's going to be adding a positive. So I went ahead and said this first one's the same thing as negative 1 over 6e to the 5th. And then I'll have plus e over 6. And that would be a fine answer. What I did is I've got a common denominator. I multiplied this second fraction by e to the 5th over e to the 5th to get a common denominator of 6e to the 5th. And then that would give me a numerator of negative 1 plus e to the 6th, better written as e to the 6th minus 1. So for the answer that I have, I'll go ahead and go to the page and set up a nice fraction to begin with. And my numerator was e raised to the 6th power minus 1, all divided by 6e raised to the 5th. We'll see if that's an acceptable format of the answer, and I figured it should be. But I'm sure any of those earlier answers I had would have also been fine. For your next one here, you have the integral from 2 to 5 of 1 over x dx. So you can say, well, whether you write it this way or this way, you need to understand that the integral answer is the natural log of the absolute value of x. And now we're evaluating that between 2 and 5. That's just going to be the natural log of 5 minus the natural log of 2. The absolute value is really irrelevant in this case, since they're both positive anyway. So you could simplify that to be the natural log of 5 over 2. I'm sure you could also say the natural log of 2.5. I'll leave it as a fraction and say it's the natural log of 5 over 2, just like that. Check answer. And it likes it. For the next one here, we have the integral from negative 2 to 0 of the function 9x minus 18e to the 3x. I like this one because it's combining one that we have to use the power rule on versus our exponential integration rule. The power rule says add 1 to the exponent, divide by that new exponent, 9 over 2 x squared. Then the exponential rule says that the integral of any exponential function is that exponential function divided by the derivative of its exponent. Well, dividing by 3 is what caused that 18 to become a 6. So now I need to evaluate that answer from negative 2 to 0. You first plug in the upper limit. The first term would be 0. The second term is going to be minus 6 times e to the 0, which is minus 6 times 1. We get a negative 6 for the upper limit. Now minus the lower limit. When you plug in a negative 2, your first term is going to be 9 over 2 times 4. So that's going to be 18 minus 6 times e to the negative 6th power. So now I can see, well, first of all, I have negative 6 minus 18. That's going to be minus 24, negative 24, I should say. Minus a negative, that's going to be plus 6e to the negative 6th. I think that's a good format for a final answer, the negative 24 plus 6. And then we have e raised to the negative 6th power. You could have also said 6 over e to the 6th. And it's liking this solution. For 21, we have an absolute value problem within an integral. You just need to remember there's no such thing as the integral of an absolute value. You have to get rid of it first and foremost. This one was pretty easy because all I said is that, well, I know that the absolute value of x, it's going to look the same on each side. It's an even function. So if I'm trying to evaluate from negative 4 to 4 of a function that is even, why not just evaluate from 0 to 4 and double it? Because the two areas are identical anyway. So that's the way I got rid of the absolute value. As I said, well, it's just the same thing as the integral of x with respect to x from 0 to 4, double. So now the integral of x from 0 to 4 gives me x squared over 2 from 0 to 4. Plug the 4 in, you'd get 16 over 2 is 8. Of course, when you plug the 0 in, you get a 0. So now I have 2 times this area of 8 for a total area of 16 for this function. We'll check that answer. And of course, it's right. When I move to the next question, I'll have to move to the next page of my work. For 22 here, again, it gives me an absolute value within an integral problem. This one, I can't just say, hey, it's twice the area from 0 to 4, because this is not equidistant from the origin with the 4. So I have to think about this a little bit more, and I say, well, the absolute value of x cubed, I know it's just x cubed whenever x is greater than or equal to 0. The absolute value does nothing. However, for values of x less than 0, the y value would go down negative. This is going to force it to go positive. It's going to be the negative of x cubed. So then I need to break apart my integral of the absolute value of x cubed and say from -8 to 0, that absolute value is serving as a negative x cubed in that region. But then from 0 to 4, the absolute value does nothing, and it's just the same thing as a positive x cubed. I integrate each of these and evaluate over their respective integrals. The first one gives me negative x to the 4th over 4 from -8 to 0. Then I would be saying plus x to the 4th over 4 evaluated from 0 to 4. This first one, when I plug in the 0, of course, I get a 0. But then you'd plug in the lower limit. And when you plug in the lower limit, you'd say, well, I know it's going to be subtracting a negative. That's why it's plus. The -8 to the 4th, still positive. 8 to the 4th over 4 gave me 1,024 there. So that makes sense that I knew that that had to give me a positive answer since it's the area under an absolute value. It did. Now for the second one, all I have to do is evaluate it at 4. I know that that'd be 256 over 4, just 64, minus the lower limit of 0. 1,024 plus 64 should give me 1,088 for the total area under this curve between -8 and 4. And you can see, fortunately, we're right. For 23, again, absolute value function. So for this one, what I did is I thought about it, and I can say, well, the cosine of x, I know is positive everywhere in your unit circle from 0 to pi over 2. From pi over 2 to pi, it goes from 0 to -1. So I said the cosine of x is greater than or equal to 0 from pi over 4 to pi over 2. And then that tells me that that absolute value, I can just ignore it in that region. I can just say this is the integral from pi over 4 to pi over 2 of the cosine of x, which is going to give me the sine of x. And then I can evaluate that integral answer of the sine of x from pi over 4 to pi over 2. So I first evaluated the upper limit. Sine of pi over 2 is 1, minus the sine of pi over 4, which is the square root of 2 over 2. Now, for the second portion of this, well, what about from pi over 2 to pi? In that region, my cosine is negative, so the absolute value is going to have to change the sign and be the negative of the cosine. So I said, in this region, that absolute value is going to serve as the negative of that cosine function. You could leave the negative on the inside of the integral or go ahead and factor it to the outside. I chose to factor mine to the outside. And the answer is going to be the negative of the integral of cosine, which is sine. Then we're evaluating that from pi over 2 to pi. You get the sine of pi is 0. Sine of pi over 2, of course, is 1. But then you're saying upper limit minus lower limit. You get your -1 on the inside. You have to change the sign of that, of course, because it's being subtracted. And so we get our +1. We knew it had to be a positive answer. It is. So we get our upper limit from pi over 4 to pi over 2 gave us an area of 1 minus the root of 2. The limit from pi over 2 to pi gave us an area of 1. That's going to give us a total of 2 minus the square root of 2 over 2, which in this case, I would prefer an exact answer, but they're wanting a decimal approximation. So as a decimal, that's 1.293 to 3 decimal places. We'll check that answer, and they like it. Up next, I I did some problems like these in the notes. They're pretty quick and straightforward. What happens when our limit of integration isn't a constant? You just plug it in as if it were. So if I'm integrating x to the 10th from 1 to b, the integral of x to the 10th is x to the 11th over 11. When you evaluate that at b, you'll just get b to the 11th over 11. Now subtract that by when you evaluated it at 1, and I have a mistake there I need to fix real quick. When I evaluate this at 1, it's not 1. It'd be a 1 for the numerator. 1 to the 11th is 1, but then that 1 is divided by an 11 as well. So I'll have b to the 11th over 11 minus 1 over 11. I'll go into my problem and enter that in. B raised to the 11th power, and I am dividing that by 11. And then I have minus 1 over 11. Should be the correct final answer. We'll check that. Ooh, it's taking a second. It's thinking about it. There we go. I was worried there for a second. Now, for 25 here, this is our one where we have the integral of 1 over x dx. Remember, whether the dx is written in the numerator or not, you can think of it this way. We know that the integral of 1 over x is the natural log of the absolute value of x. This time we're evaluating from a to 10a. No problem. It's going to be the natural log of the absolute value of 10a minus the natural log of the absolute value of a. Then you can say, well, I could condense these two down. Anytime I subtract, I divide. I'll have 10a over a. The a's eliminate, and you just have the natural log of 10. And for that, you don't even need an absolute value since 10 is automatically positive. I'll just say natural log 10 should be a good answer. And it likes it. For the last question here, I really like this one. It's asking me to evaluate the integral from -1 to 3 of f of x dx, where f of x is a piecewise defined function. So it's telling you that f of x, anytime x is less than or equal to 1, we know that it's 3 minus x cubed. So for the portion of this integral that's less than 1, I have to call it that. Well, I did. So the integral of from -1 to 3 of f of x dx is anywhere from -1 to 1, it's the top part of the piecewise function, 3 minus x cubed. However, for values of x greater than 1, the function is x squared. So for the rest of this, I had to split this up into the area between -1 and 1, and then the area between 1 and 3. From 1 to 3, it's the second function, it's x squared dx. Now we evaluate both of these. The first one integrates easily to 3x minus x to the 4th over 4, evaluated from -1 to 1. The second one just x cubed over 3 from 1 to 3. In that first one, if we evaluated it at 1, we're just going to get 3 minus 1/4. Minus, when you evaluated it at the lower limit, you're going to get a -3 for the first term, and you'll still get a minus 1/4 for the second term. That second evaluation, when you plug in a 3, you'll get 27 over 3, which is 9, minus 1 over 3. In the first group, I can see that I'll have a 3 plus 3 for 6, and then I'll have a plus 9 for 15. I was just getting the whole numbers taken care of. Then the fractions, two of the fractions cancel. You'll have a -1/4 plus 1/4. I can cancel those. I'll have 15 minus 1/3. That's 45 over 3 minus 1 over 3 for 44 over 3. Final answer. Check that answer. Correct. All right. This completes section 5.4, where we're using the fundamental theorem of calculus part 1, otherwise known as the evaluation theorem. Let me know if you have any questions through this section. Should be pretty straightforward, but I'll be glad to help you out if you should need it.